Hello everyone, my name is Huang from Wuhan University. Today, I'm gonna talk about an adaptive superpixels for vegetation detection on high-resolution images based on MLP. I will introduce it from the following aspects. The motivation. Vegetation detection is the work of determining the ground vegetation coverage. This is actually a binary classification problem. Many related algorithms have been applied to detect vegetation on remote sensing imagery, but these still have limitations in training speed and detection precision. In the past few years, many CNN architectures are taken over for detection tasks, and one remaining problem is the loss of details at boundary. In order to solve the problem of boundary details, this paper introduces adaptive superpixels with accurate boundary positioning and compact regularity. Superpixels refers to an irregular pixel block, which is composed of adjacent pixels with similar texture, color, brightness, and other characteristics. Accurate superpixels boundary can make the detection of vegetation boundary more accurate. Now, I will introduce our method. Based on the motivation to get accurate boundaries, the method has two parts, namely superpixels generation and multilayer perceptron. The first part is divided into global boundary matching and local boundary matching. The first is the global boundary matching. This step focuses on the boundary adherence in the meaningful regions. Meaningful regions are including trees, house boundaries, road outlines, and other regions with rich boundary information. In this step, the initial superpixels boundary is generated first, and then we will relabel the global boundary pixel. Relabeling is related to color feature and spatial feature. First, all boundary pixels are marked according to the equation, where the color and the distance represent the color feature and the spatial feature. The process repeats until all boundary pixels are relabeled or stops until the next queue reaches M1 queue. Then, the local boundary matching. This step focuses on the compactness of superpixels in the meaningless region. Meaningless regions are including road, grass, house surface, etc. In this step, we first filter meaningless regions based on gradient, color, and texture constraints, and then relabel the local boundary pixel. The equation of each constraint is as above, where omega t represents the texture variance, and eta g, eta t, eta c, and eta omega are various thresholds. The equation indicates that when any of three constraints is 1, edges are identified for possible relabeling using a criterion. The criterion is as above. Remarking is only related to spatial feature, so the superpixels will more compact. In this step, only the pixels that satisfy the conditions are pushed to the from queue. The process repeats until all boundary pixels are relabeled or stops until the next queue reaches the M2 queue. The next goal is to determine which superpixels are vegetation. One intuitive solution is to apply multilayer perceptron. Average features of all pixels in the superpixels are computed as the input. The complete MLP model process is divided into forward propagation and back propagation. Then, we will show you our experiment results. We tested the proposed method on the UAV dataset and the ISPRS dataset. including various numbers of images and image types. Their ground truths are all available. What we have conducted in the experiment include the comparison of superpixels and the comparison of vegetation detection. To demonstrate our method's good performance, several methods, including score and thick algorithms, are compared with. We can say the result of score is not compact, and the thick result is too regular with poor boundary adherence. On the contrary, our method can not only ensure the compactness, but also shows excellent adherence to the boundary. In order to further compare, we have made a comparison experiment with 8 other superpixel algorithms. Here are the results. Here are the details of the results. It can be found that MS shows that the generated boundary of a target is not preserved anymore. The superpixels of thick is too regular with poor boundary adherence. Other pixels also can balance compactness and adherence. However, our algorithm is shown to have strong adherence at meaningful areas, and in the meaningless areas, a high compactness can be obtained. Otherwise, our method is in general the fastest or second fastest solution for yielding superpixels. For UAV datasets, we compare the proposed SP-MLP method with pixel-based MLP models, core MLP, and thick MLP models. It can be found that the pixel-based MLP vegetation detection results are noisy, and there are some misclassification areas. The other two methods also have many force detection. However, our algorithm gives a more complete vegetation detection. Quantitatively, our method can perform best in all indexes. For ISPRS datasets, we also added a comparative experiment with CNN-based methods such as ResNet and HRNet. In general, ResNet and HRNet can yield very promising results based on large training datasets. Two CNN-based methods show misclassification when ground truth contains few false labels. However, our proposed method, on the other hand, it is more prone to keep boundaries and rarely misidentifies non-vegetation as vegetation. Quantitatively, our result is basically better than HRNet, and for ResNet, comparable performance can be achieved by our method, but the prediction model of ours is much smaller and much easier to train. Okay, let's end this talk with conclusions. What we have done, we present a method to a hybrid solution that employs handcrafted and learning-based ideas. Specifically, we introduced a method for generating boundary-advancing watershed superpixels. In particular, a two-step boundary-advancing criterion is suggested to generate superpixels. Finally, to detect the vegetation, MLP model is trained by integrating of the adaptive neighborhood superpixels. In the future, we would like to extend our work on multiple target detection. Also, study more reasonable features from superpixels of various shapes. Thank you for listening this talk.